A researcher is investigating the number of female cubs present in litters of size 4. He believes that the number of female cubs in a litter can be modelled by a binomial distribution with 4 trials, that will be the 4 cubs, and a probability of 0.5, meaning an equal chance of boy and girl cubs. He randomly selects 100 litters, each of size 4, and records the number of female cubs. The results are recorded in the table below. So we can see the number of female cubs here, 0, 1, 2, 3, and 4, and the observed number of litters, which should add up to 100. He calculated the expected frequencies as follows, and of course that is using the binomial for 0.5. What we need to do is work out the probability and then multiply it by 100. And because it's symmetrical, the R is in 2 places there. So we want the probability that under the binomial model, there's 1 female cub. Now you can do that if you have a calculator that will calculate that for you. You can do it just on a scientific using 4 choose 1 times 0.5 times 0.5 cubed, which of course just becomes 0.5 to the power 4. And if you work that one out, and I'll just do that on my scientific. So we have 4 choose 1 times 0.5 to the power 4. You'll see that that is 0.25. And then I need to do that probability times 100 because he has 100 litters that he's looking at, giving me 25, which will go here, and 25, which will go there. And of course, you can then do 4 choose 2 times, it'll end up being 0.5 to the 4 for the middle, and multiply that one by 100. And if you do that, you'll find that that is 37.5, and they should all add up to 100. We're now asked to carry out a suitable test at the 5% level of significance to determine whether or not the number of female cubs in a litter can be modelled by a binomial for 0.5. You should stipulate your hypotheses and the critical value used. Well, let's put down our null hypothesis. That is that the binomial for 0.5 is a suitable model. The alternative hypothesis then will be that a binomial for 0.5 is not a suitable model. And to test this, for this type of data, we would use a chi-squared. And that means I'm going to use observed, take away expected, squared, divided by expected, and we want the sum of that over all of the values. So we look at our first value. The first observed is 10. The first expected is 6.25. So we are going to have 10 take away 6.25 squared divided by 6.25. The next value across is 33 in the observed and 25 in the expected. And then the next one is 33 take away 37.5 squared over 37.5. And then we continue like that. So the next one's 15 and 25, and then we've got 9 and 6.25. So we'll just calculate those. So we have 15 take away 25 squared over 25. And finally, we've got 9 take away 6.25 squared over 6.25. We can calculate each of these. This one comes to 2.25. This one is 2.56. 0.54 for this one. 4 for this one. And 1.21 for this one. And obviously we want the sum of those. So we're going to add them up, and that's 10.56. That's our test statistic, and we need something to compare it to. So the degrees of freedom here, because we had the 5 columns, is 5 take away 1, which gives us 4. And we need to identify the critical value. Now we had 4 degrees of freedom, so we're looking across here, and we want the 5% value, and that is going to be 9.488. So we can see that 10.56 is more than 9.488, and that means it is significant. And that gives us evidence that our binomial model, that was a binomial for 0.5, is not suitable